We're able to stay at the same altitude in flight when the weight of our aircraft is being countered by an equivalent amount of force in the opposite direction. Here, our lift needs to equal our weight. In straight and level flight, these two forces are acting in opposite directions. The way our airplane turns is by banking its wings. Lift is deflected to the side we're banking. Weight, on the other hand, can be thought of as a product of gravity. Gravity is always pulling us towards the same place, the center of the planet. Gravity doesn't care which way our wings are banked, and so if we stay in a coordinated turn, our weight will always be moving in the same direction. What this means is that in a bank, we're not using all of our lifting force to counteract that weight. Only a portion of that lift has a vertical component, which is counteracting weight. And that vertical component of lift gets smaller the steeper we bank the aircraft. When we have less lift to counteract weight, we won't be in equilibrium and won't be able to maintain altitude. In order to maintain altitude in a turn then, we need to increase lift, generally by increasing our angle of attack. Doing so increases our total lift, so we have more of it in our vertical portion and can maintain altitude. Notice here that we've increased angle of attack and that there's only so much we can increase that angle before hitting the critical angle and risking a stall. If we bank the aircraft more, we once again lose sufficient vertical lift to maintain equilibrium. Total lift will have to increase once again by raising the angle of attack, and now we're even closer to that stall angle. It wouldn't take a very large decrease in speed right now to stall the aircraft. A small speed reduction would require a higher angle of attack to maintain lift, which could bring us into a stall. There's a direct relationship then between the angle of bank in a level turn and the stall speed of our aircraft. Let's plot the bank angle of our aircraft on a horizontal axis of a chart, from a wings level 0 degrees all the way through a full 90 degrees of bank. On the vertical axis, we'll have our stall speed, and specifically the percent increase in stall speed from VS, or the wings level stall speed. What we see is that stall speed increases as the wings are banked more in a level turn. The increase in stall speed is very pronounced at bank angles over 60 degrees. As we said, our stall speed increases because we're increasing angle of attack. We do this in order to increase lift. Our banked aircraft needs to produce more total lift just to do the same job of counteracting weight. So even though we may not be climbing with this extra lift, our load factor has increased because weight has stayed the same. This means we can also plot a relationship between our bank angle in a level turn and our load factor. And it looks like this, also making a dramatic climb at higher angles of bank. In a level turn approaching 90 degrees of bank where we remain coordinated and aren't, for example, using rudder authority and thrust to maintain altitude the way a fighter jet would, we could experience load factors approaching infinity. Let's zoom in on this graph and look at some of the more realistic scenarios. If our aircraft starts at wings level, our stall speed may be represented by the bottom of the green arc of the airspeed indicator. Here it's 50 knots. If we raise our bank angle, both our stall speed and load factor increase. At 45 degrees of bank, we find ourselves here on the chart, around a 20% increase in our stall speed, which has brought it from 50 knots to 60 knots, and an increase in load factor to about 1.4 Gs. If we increase our bank angle some more to 60 degrees, we've gone to around a 40% increase in stall speed. It's now about 70 knots, and a load factor of 2. We've had to double our lift at 60 degrees, so we feel twice as much loading. The math on these relationships is that our stall speed increase is equal to the square root of our load factor. So here, with a load factor of 2, the square root is about 1.41, which gives us a 41% increase in stall speed. All of this serves to demonstrate the fact we hear so often from our flight instructors that the airplane can stall at any speed. Here in straight and level flight, we should be able to reduce power, pitch up, and maintain altitude. We're not turning, so we aren't having to increase total lift, and we're at a load factor of just 1 G. Our stall speed is unaffected, and we should find it as we approach the bottom of the green arc, where we begin to hear a stall warning, and finally the aircraft stalls. We'll recover from that stall and regain 2,000 feet of altitude, and try something else. Let's enter a turn to the left and practice our steep turns. We'll take our bank angle all the way to about 60 degrees, well past what we need to demonstrate in our check rides, but from our graph before, we know that in level flight at 60 degrees, we're at 2 Gs, and our stall speed increases about 40%. If we reduce power and continue to pull back to maintain altitude, we hear that stall horn a lot sooner now. The aircraft enters what's considered an accelerated stall at around 70 knots, well higher than where the bottom of the green arc is. Now, if you've got good attention to detail, you've heard us mention a few times that all these relationships between bank angle and load factor and stall speed hold true in a level turn, when the aircraft needs to increase lift to maintain altitude. If we're in a large bank but we're not increasing lift to maintain altitude, we won't experience these same increases in load factor and stall speed. Let's pitch down to gain some speed and try something. We'll pitch up to climb, and with the nose in the air and no longer pulling back, let's bank the aircraft again. If we don't put any pressure on the elevator, the aircraft will drop in altitude, and quite rapidly, but notice at a very extreme bank angle, we don't hear that stall horn go off. We can't feel the load factor on the sim here, but we wouldn't notice a great increase in Gs until we actually come out of this dive and pull back on the stick. Keep all this in mind when flying the traffic pattern, and especially if executing a circle to land instrument procedure, which requires us to maintain altitude and make turns to align with the runway. Take extra precaution that we're not getting too slow on those approaches, as we can experience accelerated stalls at speeds in excess of the listed VS and risk a loss of control incident close to the ground. This brings us to a final point to make about accelerated stalls. Let's say we're practicing that move again with that knife edge descent, but we're a bit close to the ground. When we want to pull out of it, we get a bit aggressive and pull way too hard back on the stick. If we don't first break the wings in half, we'll hear our stall horn go off at a very high speed and enter a stall spin rather quickly like this.